In this video, we are looking at something called zeros and their multiplicity. So first, let's talk about zeros. So if we have a polynomial function f of x equals x squared minus x minus 6, and we want to factor it completely, we would get f of x equals, so there's going to be a factor of x minus 3, and there's going to be a factor of x plus 2, because we're looking for numbers that multiply to be negative 6 and add to be negative 1, and that would be that. And then we'd use something called the zero product property. The zero product property basically says if you have two numbers that multiply to be 0, then either A equals 0 or B equals 0, or both, because that's the only way that you can multiply two numbers to get 0. And so with that, if this whole thing is equal to 0, then we know that either x minus 3 is 0 or x plus 2 is 0, and we would find that the zeros of this polynomial would be x equals negative 2 and x equals 3. These two numbers represent the real zeros of f. And so a couple notes. In real zeros, if your function evaluated at the value of your real zero, so if I plug negative 2 into f here and it equals 0, that means that that number is a real zero. The number r is an x-intercept, or the x-coordinate of the x-intercept, right? It would be r comma 0. The factor, or this binomial x minus r, would be a factor of f. So we saw that 3 was a factor, negative 2, or 3 was a 0, negative 2 was a 0, so it's x minus this 3, and this can be thought of as x minus a negative 2. So those would be our factors, and we also call r a solution. R is a solution. So in this example, we're trying to construct a polynomial in standard form that has a degree of 3, and whose zeros are negative 3, 2, and 5. So if these represent zeros, then I know that a factor of my polynomial would be x minus, and then whatever the value of my 0 is. So it'd be like x minus a negative 3, x minus 2, x minus 5. So I'm going to start by writing my polynomial in factored form. So it's going to be x minus negative 3. So when you subtract a negative, we can just add. Then it's going to be x minus 2 and x minus 5. So this is called factored form, but we want this in standard form. So standard form requires us to expand this. So what I'm going to do is I'm going to take these first two binomial groups and I'm going to expand them. I'm going to FOIL. So I'm going to take x times x and then x times negative 2 and multiply those. So x times x is x squared. X times negative 2 is this negative 2x. Then I will take my 3 and I'll expand that through. So it'll be 3 times x, which is 3x. And then 3 times negative 2, which is negative 6. All of this is still being multiplied by this x minus 5. But what we'll do first is clean this up, combine some like terms before we multiply again. So it's going to be x squared plus x minus 6 times x minus 5. Now we'll distribute again. So we'll take this x squared, multiply the x, and then take the x squared, multiply the negative 5. So that's going to give me x cubed minus 5x squared. Then I'll move on to the next term and multiply the x through. So x times x is x squared. And then x times negative 5 is negative 5x. And then lastly, I'll move on to my negative 6. So negative 6 times x and negative 6 times 5. So that's going to be a negative 6x. And a negative 6 times negative 5 is positive 30. And then to get my standard form equation, I just have to go through and combine my like terms. So f of x will equal, there's only one cubic term, so it's x cubed. I have a negative 5x squared and an x squared to give me negative 4x squared. Negative 5x and negative 6x combined to be negative 11x. And then ultimately it will be plus 30. So this is my third degree polynomial whose zeros are negative 3, 2, and 5. So if I were to take these numbers and plug them in for f, you would see that each of those numbers would make this polynomial 0. All right, so zeros. We know that zeros are found from factors. And so if you have a polynomial that's already in factored form, that's really nice because we can quickly and easily identify the zeros. Basically, the zeros are just what's going to make each of these factors be equal to 0. So I know from x minus 2, I'm going to get a 0 of positive 2 because if I set that equal to 0, I could just add 2 to both sides. From this, I'm going to get a 0 of negative 3. again, for the same reason. And from this, I'm going to get a 0 of positive 1/2. Now, multiplicity, when we talk about multiplicity, it basically talks about how many times this factor or this 0 is represented in your polynomial. And the way that we can figure out multiplicity is based on the power of your factor. So since this x minus 2 really just has like a power of 1, its multiplicity will be 1. This x plus 3 has a power of 2, so it will have a multiplicity of 2. And then this x minus 1/2 has a power of 4, so it will have a multiplicity of 4. Now, when you have linear factors like this, so all of them is just like inside it's x to the first, x to the first, x to the first, you can actually calculate the degree of your polynomial by just adding these multiplicities. So if you add 1 plus 2, that's 3, plus 4 is 7. So this polynomial actually has a degree of 7. Now, another thing worth noting is if you have a 0 that has an even multiplicity, like x equals -3 and x equals 1/2 do, that means that your graph is just going to touch the x-axis at those values. Whereas if your graph has an odd multiplicity, it will actually cross through the x-axis. So at x equals 2, your graph, like if you have the x-axis here, your graph is going to cross through the x-axis like this, versus at x equals -3, your graph is just going to come and just like touch the x-axis like that without actually crossing through. Okay. So in this next example, we have this factored form of this polynomial here. We want to find the x-intercepts, also known as the zeros, and then for each of them determine whether it has an odd or even multiplicity so we can know if it touches or crosses. So if I take this first factor and I set it equal to 0, I would find that I have a 0 at x equals -1, right? That's what makes this 0. And at x equals 2, I'm going to have another 0. The multiplicity on my first group is 2, and on my second group is 1, because remember, those just come from the powers of your group. And like we said before, if it has an even multiplicity, that means that my graph just touches at that x value, and so then it will cross here. And so if we're talking about the degree, this has, again, they're linear factors, like it's x to the first and x to the first. So I can just add the multiplicities, and this is a cubic, essentially. So if I were to expand this out, it would be something x cubed. Now, one thing to note is in a polynomial function, it will have at most n-1 turning points. So if it's an nth degree polynomial, like a 5th degree polynomial, it can have at most 4 turning points. Now, it could have less than 4 turning points, but it will have at most n-1, or at most 1 turning point less than the degree. So if we're looking at this is an even degree polynomial with a positive a value, notice that this has 1, 2, 3, 4, 5 turning points, which means the degree of this is at least 6, right? At least 6. Now, when we describe something called end behavior tells us what our graph is doing at the large values of x in both directions. So as I move out on the x-axis, as my x values get really large, what is my y value doing? So even degree polynomials always start and end in the same direction. So as x is really negative and x is really positive, they're going to be going in the same direction. If you have a positive leading coefficient, a positive a value, it's going to start and end up. So how do we describe end behavior? Basically, we describe end behavior by talking about what happens when x approaches positive and negative infinity. So you'd say, like, as x approaches positive infinity, what's happening to f of x? My function, the y values. And if it's a positive a value, as x gets really large, we notice that my y values are going up, so they will also be going to positive infinity. And as x goes to negative infinity, as x is going to negative infinity, since this is an even degree polynomial with a positive a value, it will also go to positive infinity. So note, in even polynomials, the end behavior matches in both directions, right? So like you can see in this one, as x is going to positive infinity, my y values are going down. So as x goes to positive infinity, my y values, which is f of x, is going to negative infinity. And also the same thing is happening as x goes to negative infinity. as x is getting really small, my f of x is also getting really small, right? It's going off to negative infinity. But with odd degree polynomials, they start and end in opposite directions. So if you have a positive leading coefficient, right, if your a value is positive, it'll start low and high. So it starts as x goes to negative infinity, right? As x is going to negative infinity, your function's values, your y values are also going to negative infinity, right? So as x is getting really negative, my graph is going down. And then as x goes to positive infinity, f of x is going to be going to positive infinity. So these start and end in opposite directions. So it starts low, ends high. And then if it's an odd degree with a negative a value, it's going to do the opposite. So as x goes to negative infinity, negative infinity, you will notice that f of x will go to positive infinity. Sorry, it's going up. So as x goes in this direction, my y values go up. And then as x is going to positive infinity, my y values, right, as x goes in this direction, my y values are going down. So notice it goes high to low, right? It starts positive, or it is going toward positive infinity and then negative infinity. So it starts high, ends low. This starts low, ends high. And that is true for odd degree polynomials. They start and end in opposite directions. Whereas for even degree polynomials, they start and end in the same direction. And whether it's up or down is dependent on the leading coefficient.